Let us now discuss the basic differentiation rules and rates of change. The goals for this lesson are to help you find the derivative of the function using the constant rule, the power rule, the constant multiple rule, and the sum and difference rules. And then help you find the derivatives of sine function and of the cosine function, and then use derivatives to find rates of change. Let's talk about the constant rule. In this section, you will be introduced to several differentiation rules that allow you to find derivatives without the direct use of limit definition. So the first one is the constant rule. So the derivative of a constant with respect to x is just equal to 0. So as you see here from the graph, this is the graph of a constant function. The constant function is just a horizontal graph. When you say horizontal graph, the slope is just equal to 0. So therefore, the derivative of a constant is 0. So therefore, if you take the derivative of y equals 7 with respect to x, the derivative is just 0. The derivative of f of x equal to 0, the derivative with respect to x is just 0. Now the derivative of this function, so suppose a derivative with respect to t of fs of t, which is equal to -3, is still equal to 0. And the derivative of this expression k equals pi squared, pi is constant, k is also constant. So the derivative with respect to x is still equal to 0. Next is the power rule. The power rule is given by this theorem here. If n is a rational number, then the function f of x equal to x to the n is differentiable, and the derivative with respect to x of x to the n is equal to n times x to the n minus 1. And for f to be differentiable at x equals 0, n must be a number such that x to the n minus 1 is defined on an interval containing 0. Also, when using the power rule, the case when n equals 1 is best thought as a separate differentiation rule. That is, the derivative of x with respect to x is equal to 1, and that is actually the case when n is equal to 1. Now, as you could see here from the graph, the function y equals x is just this line here, this diagonal line here, wherein the slope is constant, and that is just equal to 1. So whenever you see x, the derivative with respect to x is just equal to 1. Now let's apply the power rule to the following exercises. First, let's differentiate f of x equal to x cubed. Now the derivative of f of x equal to x cubed with respect to x is equal to, so this power here will be copied, so you copy 3, that's how you have 3 here, and then you subtract 1 from the exponent, so that's how you get 2 here. Next, if you're given g of x equal to cube root of x, you can still use the power rule here by first rewriting this expression here as x to the 1/3. So cube root of x is also equal to x to the 1/3. And then from there, you differentiate that expression. So differentiating x to the 1/3 with respect to x, you can use the power rule. So first you copy the exponent, that is 1/3, and then you subtract 1 from the exponent. So you have 1/3 minus 1 is equal to -2/3. Therefore, this is equal to 1 over 3 times x to the 2/3. Remember, for loss of exponents, if you have negative exponents, you can in the numerator, you can bring that down to make the exponent positive. Another example, let's differentiate 1 over x squared. Now we still can use power rule here if we rewrite 1 over x squared as x to the negative 2. So if you see something like this, you can just rewrite this as x to the negative 2 and then use the power rule to get the derivative. Now differentiating this with respect to 2 and using the power rule, you get negative 2. So you copy the exponent, you have negative 2, and then you subtract 1 from the exponent here. So that is the exponent of the derivative. So you have negative 2 minus 1 is negative 3. And since we have a negative exponent, we can just bring this one down, put this in the denominator to make the exponent positive. So this expression is equal to negative 2 over x cubed. Next, the constant multiple rule. So for the constant multiple rule, if you have a constant times a function, you can just take out the constant and then differentiate the function. Now let's apply the constant multiple rule to the following examples. Let's differentiate y equals 5x cubed. First, let's take out 5 and then differentiate x cubed. To differentiate x cubed, you just use the power rule. Copy 3 and then subtract 1 from the exponent here to get 2. So therefore, simplifying this, you get 15x squared. Second example, you have y equal to 2 over x. First, we will rewrite 2 over x as 2 times x to the negative 1. Then, you can take out 2 and then differentiate x to the negative 1 with respect to x. Differentiating this, we can use the power rule. So you copy first the exponent, which is negative 1, and you just multiply that to the constant. So you have 2 times negative 1, and then subtract 1 from the exponent here for the exponent in the derivative. So you have negative 1 minus 1 is negative 2. And then simplifying this, you have negative 2. And then since we have a negative exponent here, we can bring that down to make the exponent positive. So the derivative of y equals 2 over x is equal to negative 2 over x squared. Next, let's differentiate f of t equal to 4t squared over 5 with respect to t. Using constant multiple rule, we take out 4/5 because we know that we can rewrite this 4t squared over 5 as 4/5 times t squared. Then when we differentiate this, we take out 4/5 first and then differentiate t squared. The derivative of t squared is just 2t. Copy 2, bring down 2, and then subtract 1 from 2. That's how you get 1 in the exponent here and 2 in the coefficient. Then multiplying this 2, you get 8/5 t. So that this is the derivative of this function here with respect to t. Now let's differentiate 2 times square root of x. Now differentiating this, you have to rewrite first square root of x as x to the 1/2. So we have 2 times x to the 1/2. And then take out 2 and then differentiate x to the 1/2. The derivative of x to the 1/2 will just be 1/2. Copy the exponent and then subtract 1 from the exponent here. Subtract 1 from 1/2. That's how you get negative 1/2. And then multiplying this 2, the 2 will just cancel out. So you have x to the negative 1/2, which is the same as 1 over square root of x. Next, find the derivative of 1 over 2 times the cube root of x squared. The first step is to write this in exponential form. You can rewrite this as 1/2 times x to the negative 2/3. And then take out 1/2, then differentiate this. The derivative of x to the negative 2/3 is just negative 2/3 times x to the, now subtract 1 from negative 2/3, that gives you negative 5/3. So this is equal to, if you simplify this, the 2 cancels out, so you have negative 1/3. This is now equal to negative 1 over 3 to the 3 times x to the 5/3. Lastly, let's do y equals negative 3x over 2. You can rewrite this expression as negative 3/2 times x, and then take out negative 3/2, and then just differentiate x. The derivative of x is 1. So therefore, this is equal to negative 3/2. Now, from the examples, we've seen that the constant multiple rule and the power rule can be combined into one rule. The combination rule is equal to this. The derivative with respect to x of cx to the n is equal to cn x to the n minus 1. Now let's talk about the sum and difference rules. So if you want to differentiate the sum of two functions, you can just distribute the differentiation operation inside this parenthesis here. So the derivative of the sum is equal to the sum of the derivatives. And the same also for the difference. The derivative of the difference of two functions is equal to the difference of the derivatives of the function. That means that if, for instance, if we are going to find the derivative of f of x equal to x cubed minus 4x plus 5, to get the derivative, you just differentiate each term. That is like distributing the differentiation operator on each term. So the derivative of this function is just the derivative of the first term, which is 3x squared, and the derivative of the second term is negative 4. The derivative of this term, 5, is 0. Here, let's differentiate this. So to differentiate g of x equal to negative x to the 4th over 2 plus 3x cubed minus 2x, you just differentiate each term. Derivative of this is equal to negative 2x cubed. So you take out negative 1/2 and then differentiate x to the 4th. You have 4x cubed. And then simplifying that, that's how you get negative 2x cubed. Here, differentiating this, you get 3 times 3. So that is equal to 9. And then subtract 1 from the exponent here. That's how you get 2. So 9x squared is the derivative of 3x cubed. And then the derivative of negative 2x is equal to negative 2. This example. Now, for this next example, we still have not discussed how to differentiate a rational expression. So all we need to do is to divide each term by x. So you have 3x squared divided by x is 3x. And then negative x divided by x is negative 1. Then we have 1 over x. So we have 1 over x here. And then write this in exponential form. You can write this as x to the negative 1. Then you can now differentiate each term. The derivative of 3x is 3. The derivative of 1 is 0. And then you differentiate 1 over x, but 1 over x is just x to the negative 1. Now the derivative of x to the negative 1 is equal to negative 1 over x squared. Then you can simplify this into this. Now let's discuss the derivatives of sine and cosine functions. The derivative of sine x with respect to x is equal to cosine x, while the derivative of cosine x with respect to x is equal to negative sine x. Now let's apply that to here. All other properties will hold or will apply in this case. So if you differentiate y equal to 2 sine x, this is the same as the constant multiple rule. So you take out 2 and then differentiate sine x. Derivative of sine x is cosine x. So the derivative is just 2 cosine x. Next, the derivative of sine x over 2. You can take out 1/2 and then you have sine x. And then take out 1/2, differentiate sine x to get the derivative of y. So y prime is equal to 1/2 cosine x because the derivative of sine is cosine. And if you simplify this, this is just equal to cosine x over 2. Next, let's differentiate y plus cosine x. So you can also use the sum rule. So this differentiate each term. So the derivative of x is 1 and the derivative of cosine is negative sine x. Now we have y equal to cosine x minus pi over 3 sine x. The derivative, to get the derivative of this function, y, the derivative of y is y prime, derivative of cosine x is negative sine x. Here you copy pi over 3 and also the sine, so you copy negative pi over 3 and then differentiate sine x, which is cosine x. Then we'll discuss rates of change. Now in our discussion, you have seen how the derivative is used to determine slope. The derivative can also be used to determine the rate of change of one variable with respect to another. Applications involving rates of change occur in wide variety of fields. A few examples are population growth rates, production rates, water flow rates, velocity, and acceleration. A common use for rate of change is to describe the motion of an object moving in a straight line. In such problems, it is customary to use either a horizontal or a vertical line with a designated origin to represent the line of motion. On such lines, movement to the right or upward is considered to be the positive direction, and the movement to the left or downward is considered to be in the negative direction. The function s that gives the position relative to the origin of an object as a function of time is called the position function. So if over a period of time, delta t, the object changes its position by the amount delta s, which is equal to s of t plus delta t minus s of t, then by the familiar formula, which is rate equal to distance over time, the average velocity is defined as the change in distance over the change in time. So this is just a formula for the average velocity. For example, a billiard ball is dropped from a height of 100 feet. The ball's height s at time t is the position function here. S here is measured in feet and t is measured in seconds. Now find the average velocity over each of the following time intervals. So for the interval 1, 2, the object falls from the height of, so let's first get the change in s, the change in the position. So you have s of 1 is equal to, just evaluate the function at t equals 1, you get 84. And then at s equal ss, evaluate the position. What's the position of the object at t equals 2? So s of 2 is equal to 36 feet. So the object falls from the height of 84 feet to 36 feet. And then to get the average velocity, you just get the change in height. So you start from 84 to 36. So this is your second position. So you have 36 minus 84 divided by 2 minus 1. That is equal to negative 48. So 36 minus 84 is negative 48 divided by 1 is negative 48 feet per second. That's the average velocity. Now, so for the interval 1 to 1.5, so we know that the object falls from the height of 84 feet. We already have calculated that previously. This is s of 1. Then we will then compute s of 1.5. So this is equal to 64 feet. So we know that the object falls from 84 to 64 feet. So this is the second position. Then the average velocity is equal to 64 minus 84. That this is the change in s over the change in t. So 1.5 minus 1 is equal to 0.5. Simplifying this, you have negative 40. So you have negative 40 feet per second. That's the average velocity for that interval. And then so for the third interval, 1 to 1.1, the object falls from a height of 84 feet. This is at s of 1 to a height of, then you evaluate s at 1.1. That is equal to 80.64 feet. Then the average velocity using this formula is equal to, you have 80.64 minus 84, that is equal to negative 3.36. And then 1.1 minus 1 is 0.01. Simplifying this, you have negative 33.6 feet per second. Now note that the average velocities are negative. This indicates that the object is moving downward. So in general, if s, which is equal to s of t, is the position function for an object moving along a straight line, the velocity of the object at time t is equal to this. That is just the limit of s of t plus delta t minus s of t over delta t as delta t approaches to 0. This looks familiar. This is just the definition of the derivative of s with respect to t. So the velocity function is just the derivative of the position function. Now the velocity can be negative, 0, or positive. So if this is the velocity function, when you say velocity, that means that it has direction. It has magnitude and direction. So therefore, the speed of an object is just the absolute value of its velocity at that point. So the speed cannot be negative. Now, the position of a free-falling object, neglecting air resistance under the influence of gravity, can be represented by this expression here, where g here is the acceleration due to gravity, and the t is time, v sub 0 is the initial velocity, and s sub 0 is the initial height of the object. And then on Earth, the value of g is approximately equal to 32 feet per second. Or if you're using meters per second, that is equal to 9.8. So the value you put in for g is either 32 feet or 9.8 if you're going to use meters per second. Let's consider the problem here. At time t equals 0, a diver jumps from a platform diving board that is 32 feet above the water. The initial velocity of the diver is 16 feet per second. When does the diver hit the water, and what is the diver's velocity at impact? Now, let's begin by writing an equation to represent the position of the diver. Now, using the position function that was given with g equal to 32 feet per second and your initial velocity, which is given to be 16 feet per second, and the initial position, since the diver is at the top of a platform diving board, that which is 32 feet above the water, then you can assume that the initial position is 32 feet. So therefore, you can write for the position function, you have negative 1/2 32 for g, then t squared plus, this is the initial velocity, that's 16, and then the initial position, which is 32 feet. So this is our position function. Simplifying this, we have negative 16 plus 32. Then to find the time when the diver hits the water, that is when S, or the position, is equal to 0. That is actually the ground. So therefore, we just have to let S be equal to 0 and then solve for t. So equating the position function to 0, we can then solve for t. First, let's factor out 16. 16 is a common factor here. And then whatever is left, you have to factor it out. So this expression can be factored into negative 16 times t plus 1 times t minus 2, and then equal to 0. Then you solve for t. By dividing, first you divide both sides by negative 16, or just equate each factor here to 0 and solve for t. Then you have t equals negative 1 or t equals 0. So if you equate this to 0, solve for t, you have t equals negative 1. Equate this to 0, solve for t, you get t equals 2. Now, because time is always positive, then we choose 2, which is t equals 2, to conclude that the diver hits the water at 2 seconds. Then next, we want to compute for the velocity at impact. So the velocity when the diver hits the water. So first, let's compute for the velocity of the position function at any time t, and that is just the derivative of the position function. So differentiating the position function, you get negative 32t plus 16. This is the velocity. This is now our velocity function. And then we know from our result that the diver hits the ground at t equals 2, at t equals 2 seconds. So the velocity at impact is just s prime at 2. So evaluating this velocity function at t equals 2, you get negative 48 feet per second. Now notice that for s prime of t, the unit for s is feet divided by the units for the time, which is seconds. In general, the unit for f prime of x is the unit for f divided by the unit for x.